guys! In this video we're going to talk about trig. So in previous videos and sections I said, how much do you remember about your trig? We're going to be using a lot of trig in various and sundry ways. So in this particular section, which is all devoted to trigonometric differentiation, I figured I would find everything I could think of and put it on the very first page for easy reference if you need. So the basic, of course, is SOHCAHTOA. The sine is the opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. The reciprocal identities, of course. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. That also means that cotangent would be cosine over sine, because 1 over tangent, tangent being sine over cosine, so 1 over that would flip it, as dividing by fractions means you keep the first one, swap for multiplication, and flip the second one. We also have the negative identities, the Pythagorean identities, and the cofunction identities. Though the cofunctions are a bit easier to see with the graphs themselves. And I found this neat graph that had all 6 on the same grid so you could easily see what went where. The dotted lines are the secant, cotangent, and cosecant. The solid lines are tangent, cosine, and sine. So you can see very easily that the sine and the cosine graphs are virtually identical. They're just shifted pi halves to the side. And the same for the rest. Cosecant and secant are exactly the same. They're just shifted pi halves to the left of each other. The weird ones, of course, are tangent and cotangent, but if you kind of let your eyes unfocus and focus again, you can see that they're not shifted to each other, but they are reflections of each other, and a shift as well. So if you reflect it across the x-axis, or the theta axis in this case, then shift it pi halves, you would get the same graph of cotangent as tangent. So they are all very closely related to each other. And with these graphs and the definitions themselves, we can get some interesting properties of limits and differentials. For example, the tangent is sine over cosine, right? So if tangent is sine over cosine and cotangent is cosine over sine, then their derivatives would require the quotient rule, wouldn't they? Because they are themselves a quotient. So it's little details like that that kind of add up together and makes some trig very interesting in the not way. You know, full of sarcasm and thrown things. So take it one step at a time, always. And when necessary, take a break. Relax your mind a bit. Alright? So let's focus on just limits for a second, the easy stuff. We have 2 special trig limits. As long as we're talking about as x approaches 0, then sine of x over x will be 1. And cosine x minus 1 over x will be 0. Now these are 2 special limits because they work all this way. All other trig limits work exactly the way that all other limits work. So these 2 are the outliers, and the rest will work just like always. So let's see here. Now, why do we have to have these special limits? Well, if sine of x, as x approaches 0, let's look at the graph. Sine x is the red, solid red. So sine x as x approaches 0 would be 0. And then over x as x approaches 0 would be 0. So you would get 0 over 0, which you can't work with, right? So we have to have that special limit. Otherwise, we would need something else to make it work, the squeeze theorem or something. And same thing with the cosine x minus 1. Cosine of x, the solid blue, is 1 as x approaches 0. But if we subtract 1 from that, it becomes 0. And then we would have 0 over 0. So once again, we can't work with it. So we have these special trig limits that we can work with instead. So let's look at this first example. We want the limit as x approaches 0 of sine 4x over sine 7x. Okay. A lot of the time when you're working with trig, you have to work with the trig identities or with other variations of trig to make it get into the form that you need. So if the only version of sine limit I can work with is this, then I can't work with that until I have it in that form. So the first thing that I can think of is I'm going to divide by x, top and bottom, to get it into over x form. Okay? And I can do that. You can do anything you want to any equation as long as you do it to everything. So we would get sine 4x over x over sine 7x over x. And I'm just going to keep that limit to the side for a minute so that I can just focus on this. But this does not work yet because I have sine 4x and x. I need sine 4x over 4x. So that's not going to work yet. But I can also multiply in the form of 1. I can do 4 and 4, and I can do 7 and 7. Remember, anything over itself is 1, so I just multiplied by 1, top and bottom, in different forms. So that will give me 4 sine of 4x over 4x over 7 sine 7x over 7x. And now I can actually apply the limit. So if I say that in this top part that 4x is t, and in this bottom part 7x is u, then I can say that this is 4 sine t over 7 sine u over u, and I can actually apply the limit now. So the limit, let's move this just a bit. I can actually apply the limit now. So the limit as x approaches 0 of that, so that would give me, well, I got 4, and then the limit as sine x over x is 1 as we approach 0, so that'd be times 1 over 7 times 1. So that would give me a lovely 4/7 as my final answer. So I just had to manipulate this to the best of my ability until I could actually work with that limit. Okay, so let's do another one. Let's do one that's not completely sine or cosine, shall we? How about sine and tangent, and that's should be sine 12x, and tangent x. Don't know why that got cut off, but we'll work with it anyway. Okay, so my sine 12x will be very similar to what we just did, but tangent x doesn't have a special limit, so we get to do that the old-fashioned way. So let's see here. Let's work with the definition of tangent and see if that helps us out. So we would have the sine of 12x divided by sine x over cosine x, because that is tangent, which is interesting. All right, so to divide fractions, we keep the first fraction exactly the way it is. We change to multiplication, and then we flip the second fraction, which, oh, there we go. Take a look. Sine 12x over sine of x times cosine x. All right, so this part has now been reduced to a previously solved problem, just like we did up there. Instead of 4x and 7x, now we're working with 12x and x, but the process is the same, isn't it? So we can apply the limit now. So the limit, as x approaches 0, of sine 12x over sine x times cosine x would be the exact same thing as the limit as x approaches 0 of sine 12x over sine x times the limit as x approaches 0 of cosine x. Once again, because of our limit identities and limit properties, we discussed this in chapter 2. So this first part, the limit as x approaches 0 of the sine 12x over sine x, that should give us 12 over 1 times the limit as x approaches 0 of cosine x. Well, that's not an identity and it's not a special thing, so let's look at the graph. Cosine x is the solid blue. As x approaches 0, cosine x is 1. By the graph. So that gives us 12 as our final answer. So use what you know, manipulate as much as you need to get it into a way that you know, and it'll work just fine. Now this process can take a little bit, so have patience and take as many breaks as you need to not get frustrated and annoyed. Okay, so that's just the limits. Now let's look at derivatives. So we have basic derivative formulas. So the derivative of sine is cosine. The derivative of cosine is negative sine. Derivative of tangent, secant squared. Derivative of cotangent is negative cosecant squared. So you kind of see a pattern here. A lot of them flip, and a lot of them are negative, or they are paired with their inverse or their partner, however you want to think about it, in the formula. So that's not nearly as bad as it could be. So let's take a look at this first one. If f of x is negative sine x, find the derivative of f as it applies to 3 pi over 2. Okay, well, the derivative of f of x of negative sine x, well, the derivative of sine x is cosine x. So the f prime would be negative cosine x. Okay, so then we would want to apply that to 3 pi over 2. Well, that'd be negative cosine 3 pi over 2. So once again, we could take a look at our graph here. Cosine x of 3 pi over 2 would be 0. That's easy enough. And negative 0 is still 0. Okay. So, how about if we have something like this? 3 tangent x plus 2 cotangent x. Well, all of our limit rules apply, all of our derivative rules apply, all those properties still apply. So, the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. There's nothing being multiplied here other than a constant, a scalar. And there's no division either. It's just what you see is what you get. So h prime of x would be 3 derivative of tangent is secant squared and minus 2 cosecant squared. And there we are. No problems. Of course, it's not going to stay that way. The derivative, and dy over dx, that is the same thing as saying derivative. It's just a different way of writing it. And we'll get more into that in later sections when we start talking about implicit differentiation, but that'll be a while. So, we have this lovely function. It is being multiplied. We do have a product here, so we're going to need our product rule, f prime g plus fg prime. And I'm going to say this first part is f, and the second part is g. So f prime would be negative e to the negative x. Uh-oh, what did I do? Sorry about that. And g prime, well, the derivative of cosine is negative sine. Okay, so let's put this in. So we have f prime times g plus f g prime okay, and simplify as much as we can, which isn't much. There's just not much going on here. Now we do have that e to the negative x that we could pull out if we wanted to, and we really kind of prefer sine in front of cosine if at all possible, just as tradition. So I'm going to pull out a negative e to the negative x as a GCF, and I will, let's see, that would make that positive as well. And then I'm going to write sine first, just to make it easier if I have to work with this thing later. And that was g of x, so this would be g prime of x. And there we are. So all of our rules still work. The product rule still works, the quotient rule still works, all of our pieces still works, the identities, the properties, they all still apply. So we just get to use it a bit more interestingly. So let's do another one. Okay, so here's a quotient one, and that should be 7 cosine x. I don't know why it keeps getting cut off. How strange. Alright, so this is a quotient, so we want f prime g minus fg prime over g squared. Okay, so if our top is f, then f prime would be, well, the derivative of cosine is negative sine, so that would be negative 4 sine x. If our bottom is g, then g prime would be, well, derivative of cosine is negative sine. Negative times a negative is a positive, so that would give me positive 7 sine x for g prime. So let's put this in. So we got negative 4 sine x times g, 8 minus 7 cosine x, minus f g prime. Okay, let's simplify this. as much as we can anyway. There's not much here, but we can still do a little bit. Let's see here. So we got negative 32 sine x plus 28 sine x cosine x minus 28 sine x cosine x. Okay, there we go. So those two will cancel. So we'll just be left with negative 32 sine x over g squared. So that would be 8 minus 7 cosine x squared for our full derivative. And that looks terrible, so I don't think we can simplify it any further. Okay. Let's do one more. So we want to find g double prime, so the second derivative of g of t of 4 cotangent x. Okay, well, the derivative of cotangent, if we look back, derivative of cotangent is negative cosecant squared. So the first derivative is not that bad. Negative 4 cosecant squared of x. That's not bad at all. But if we're going to find the second derivative, well, none of our formulas will work exactly. So we're going to have to manipulate this a bit to make it work. So negative 4 cosecant squared, I can rewrite as cosecant times cosecant. And we now have our product rule. F prime g plus fg prime. Okay, so our double prime of g, we're going to need f prime. Well, if our first part is f, then f prime would be, well, the derivative of cosecant is negative cosecant x cotangent x. So that would be negative times a negative is, oh god, that's too many negatives for me. So how about this? There we go. We'll do this the long way. There's no problems with the long way. And then g prime would be the other one without the 4. Okay, so f prime, let's do this. So 4 cosecant cotangent times g, which is cosecant, plus f g prime and simplify. Goodness gracious. Okay. Well, at least the first part's easy. Cosecant and cosecant would turn into cosecant squared. Cotangent. Negative and a positive is still a positive. 4, and we still got 2 cosecants, so that's still cosecant squared. Cotangent. Oh, and those are now like terms, so we can combine. So that would be 8 cosecant squared x cotangent x for our double prime. So the moral of the story, have a separate sheet with all of your identities, all your properties, all your specials, and your formulas to make it as easy on yourself as possible when you have to start manipulating all this stuff, so you can reference it as immediately as you can. There's no problems with that. Just be careful of the memorization part when it gets towards test time.